Okay, so we're very lucky to have Dr. Clayton of Los Alamos give us the lowdown on the tension between the beam and bottle experiments on the neutron lifetime. He's been at Los Alamos for a decade or more, and he's an expert on this subject. So I'll let Dr. Clayton take over now.
Great, thank you. And thanks for the invitation to give this talk. So as the title says, I'm going to talk about precision measurements of neutron beta decay, and I will sprinkle in a lot about the neutron lifetime puzzle, which is this disagreement in between some experiments. So to start, we have to start with the standard model of particle physics for completeness. So I'll say this is an extremely successful theory that incorporates our knowledge of fundamental particles and their interactions. It has 6 quarks, 6 leptons, and these 4 fundamental interactions: electromagnetic, strong, weak, gravitational. Electromagnetic and weak can be unified into electroweak interaction. There are good reviews. One that I particularly like is this particle-adventure.org, which I recommend. So basically, I'll try to step through what is needed to know about this standard model for in this context of the neutron lifetime in particular. So basically, we can start with these nucleon properties. So this on the left is a cartoon from Wikipedia, I believe, of what a nucleus would look like an atomic nucleus. So if you zoom in on, see, the red ones are supposed to be protons. So you have these composite objects are made up of a couple of up quarks and a down quark. They're bound together by gluons, which are the force mediators of the strong interaction. Similarly with neutrons, except it has a different mix of up and down, and it ends up with a charge of 0, whereas a proton is a charge of 1. In these units, the masses are roughly here, about a GeV per c squared in these units. And the important thing to note here is that the neutron mass is a little bit heavier, a little bit higher than the proton mass. The proton has not been observed to decay as far as we know, whereas the free neutron, when you pull it out of this nucleus, decays in an average of about 15 minutes. So neutrons, these decayed by the weak interaction of the standard model. So it decays into this proton, electron, and anti-neutrino. And one of the interesting things about the weak interaction is it does not conserve this symmetry called parity. So basically, if you take a neutron here, and the green arrow is supposed to represent the spin direction, which is one of its quantum particles, and you would have a neutrino fly from one direction, an electron in another, and then I don't draw the proton here. That's left over after the decay. So if we invert all the spatial dimensions, the spin doesn't invert, but these momenta do, then what we find is the rate on the bottom here is not the same as the rate on the top. And so the strength of these two things is different. And so it means parity violation is not conserved, and the mirror world is different in this way. So just going forward with this kind of asymmetries. So there are a number of neutron beta decay observables that you can consider. There's a good review in Revmont Phys from Dubbers and Schmidt about this. So one of the key observables would be the mean lifetime, just the average lifetime before it decays. And you, in addition, can form many different combinations of these various vectors involved in the problem. So you have this neutron spin direction, the electron outgoing momentum, and the electron spin. Similarly with the neutrino and also the proton. And so then these factors here just parameterize kind of the strength of these correlations. And that goes into this differential decay rate where they would all figure in. So you'd have this, various asymmetry, electron asymmetry of one kind and another kind here with A, which is the neutron spin direction, and then the outgoing electron momentum, for example. And this, you can also have ones that are, it turns out, 0 in the standard model, like this D, big D, this triple which is also interesting to study. So But basically, to go further, we should consider the neutron beta decay at the quark level. So again, this is the Feynman diagram that I'm showing here. So neutron goes to a proton. This is the mediator of the weak force. One of them, the weak, are the W boson. And then you have this outgoing electron and anti-neutrino. So this interaction is very similar to muon decay, which also proceeds via the weak interaction, similarly with the W minus. And so basically, you can consider the rate of these two reactions, and you get something like at the quark level, which do not have any structures. So you have these quark states, and then you get this so-called V minus A interaction, this vector minus axial vector. The leptons are particularly easy in this case. It's the same at the quark level as that. One thing I had to sneak in here for quarks, though, is this VUD. But otherwise, it's the same as for muon at this level. So the reason for that VUD term, it's a number. It's basically because the weak states, the quark states that participate in the weak interaction are not the same as their mass eigenstates, you could say. So you have to do a rotation, and that's parameterized by this sort of rotation matrix, where that term represents kind of the amplitude from going to an up to down quark in a way. So that has to be put in to make this correct. And one property of this sort of rotation is that the sum of the squares of any of these rows or columns has to be 1, and that's an expression of unitarity as a result of unitarity. And that will figure into tests that we could do using our neutron observables. So if we go to the actual objects that we have in an experiment, which is more like a proton and a neutron, then because these are composite objects, we have to introduce more complication into that first current term. And so mainly that's done by this form factor GV and this other one GA. So GV is 1 by a conservation law. GA is nearly 1 by a near conservation law. And then this other term you can relate to electromagnetic properties. And so that's well determined. So basically the other terms that might have appeared are forbidden in the standard model, or we can neglect them at these low energies. And essentially a single parameter, this GA, or it's often expressed as this ratio GA over GV, accounts for the nucleon structure that we're interested in. Okay, so with that, you can form this relationship between this VUD, just kind of turning it around, so putting the rate 1 over the lifetime on the right here. And you get this VUD squared equals this number, which has everything folded in the phase space, all that sort of thing. And then tau, which we can measure, GA, which we can measure, and this RC, which is about 4%, which can be calculated by theory using the standard model. And we just call this the master formula, and I'll refer back to this a few times here. So to get that GA, as I was saying, there are various ways to measure it. It's most precisely determined at the moment by measuring that big A parameter that's polarizing a neutron and watching how many electrons go along the spin direction versus the opposite direction, and taking that, basically coming up with this correlation. And from that, you can use this relationship to determine lambda, which is this G over GV. There are upcoming experiments at Oak Ridge in particular that's going to measure little a to a similar precision and get lambda as well from that. But there have been various measurements over the years. So GA is somewhat well known from these experiments. And so this is the point as far as a standard model test using neutron decay. So basically this VUD from experiments, we can test that unitarity of the CKM matrix, or I call it self-consistency of the standard model in a way. So basically taking these two inputs from experiment, this is from theoretical calculations, and then you can form this delta CKM would be the degree to which it violates this unitarity relationship. And kind of the interesting thing in the last few years, it turns out we're in violation of this unitarity. If we take this VUD from nuclear decay, which is a little bit different, it doesn't depend on GA at all. However, they report a very precise value of VUD. So taking the sum of squares of these, we actually get about a 3.5 sigma disagreement with the standard model. So the advantage with neutron decay is that it's clean and the systematics are independent from the nuclear decay that goes into this. And so in that way, we can try to test this, because this is a possible signature of a violation of the standard model, which would be quite interesting. Or it's a mistake in the experiments or a mistake in the radiative corrections. So the neutron lifetime in particular also figures into Big Bang nucleosynthesis. So this is kind of the cartoon of the history of the universe, starting with the Big Bang and then have this rapid inflation. And where neutron decay rate figures in is about at the 1 second level is what I was aiming for here. And so this is when you have the universe is dense and hot enough that this reaction can goes in both directions, this and permutations of it that you can imagine. So basically I have neutrons and protons converting into each other back and forth. And so the impact of that is on nucleosynthesis, in that as the universe continues to cool, then it's the forward reaction, the neutron go into a proton more than rather than the reverse that can happen. And so at that point, the neutrons which are bound up into helium nuclei, those are the ones that survive later on. And then that can be measured by observations. And so as an input to models of Big Bang nucleosynthesis, then this determines basically how many are survive to be bound up. And this is just showing the somewhat recent Big Bang nucleosynthesis model, the standard model of Big Bang nucleosynthesis, I think they call it, and basically just running it forward and showing the impact of neutron lifetime. So it has to be good enough for that calculation. They need basically 1 or a few seconds or better in order to be not a problem here for this prediction of the helium-4 mass fraction. And the other thing you can do is turn it around and compare this prediction to the observed primordial helium abundance. So this is probably obvious, but we need both precision and accuracy. Precision being the spread of the different trials. Here it's like a BB gun target or something like that. So just imagine repeated measurements. So if they're all on a nice cluster, then you'd say, hey, I have a precise experiment. What we don't know, however, is this bullseye. We have to try to design an experiment that is accurate. And basically, we have to come up with, devise all the systematic corrections we can in order to get an accurate measurement. And in the end, we hope we're on target. We don't actually know this target, but we do the best we can to systematically correct it and get accurate measurements. And the systematics themselves will have some uncertainties. So then in general, that'll smear out this blob as well. And basically the length of the arrow, you could say, is not known exactly. So different experiments may have completely different systematic corrections. And this is a reason to do different experiments, one argument for it. Because if the corrected results agree, then it gives us some confidence we know what we're doing, basically. If they don't agree, then, well, that means we better look pretty closely. And another maybe truism, the bigger the systematic correction, the better it needs to be understood. Okay, so in that light, so here's the world average of neutron lifetime measurements over the years, so by publication years. So the particle data group is like the co-data for particle physics. They try to summarize the state of the field for various particle physics measurements. And basically, you can go back to 1960s for the first of these. And it's a pretty rough measurement. That's okay. They're just learning how to do that. They get better and better. And as you can also see, well outside the error bars, the trend is going down. And this may argue for blind experiments, or I don't know, it could be that the technique changed. And probably the technique change is what happened in the 1990s as the experiments got much better. So for example, the ultracold neutron bottles started to get results in the 90s that were quite precise. In the 2000s, even more so. In 2005, there was a bottle lifetime result that was down about here. If you can, hopefully you can see my arrow here, my pointer. And probably disappeared. And basically that wasn't accepted for several more years because it was an outlier at that point. However, I'll talk about this a little bit later. Eventually that became, it turns out was correct. And then other measurements came in line with that. And now the new accepted value is around here. Okay, and there are basically two techniques, two main techniques that are used to measure tau precisely in this kind of modern era. And there are other cool ideas, but right now they're not competitive as far as the precision. So basically, you have the cold neutron beam experiments that use pretty intense sources of cold neutrons. So in this case, say the neutrons come from the right up here, travel through this fiducial volume, that is the volume that your counter is looking at, and we look for the decay products. So whether it's the proton coming off or the electron, or even both. And then that beam continues through this thin neutron detector. So the essential trick with this technique is that you have a detector that depends on 1/over velocity of the neutron, and the neutron spends 1/over velocity time in your fiducial region. And so when you divide these out to get the branching ratio, then velocity cancels and you can use a broadband of velocities in your beam. And that's quite important for rate. And I'll show that in a minute as well. The alternative technique that's had about several experiments lately is this ultra-cold neutron bottle experiment. And the cartoon version is this: you fill a bottle, you hold your neutrons for some period of time, in general, 2 different periods of time at least, and then you count the survivors at the end. So here you fill it, hold it for a short time, count the survivors. Here you fill it the same way, hold it for a longer time, and count the survivors. And so with different holding times, you would trace out this exponential decay. So you could, instead of counting it directly, you could detect the decay products, but that just carries the total rate anyway. It doesn't, it should not give you a different rate than this. And so here's where the neutron lifetime puzzle is at the moment, that these two techniques seem to give different results. So, probably the immediate guess would be unknown systematic errors, but I think that remains to be seen. So we have these beam lifetimes up here. So this was, I believe, at the ILL, and then this one was at NIST in Gaithersburg. So these are the same technique, actually. They both have proton traps. So they count the protons coming off of a neutron beam, essentially. And the problem is they're sitting up here at around 888 seconds. All of these modern neutron lifetime experiments, they really want a lower value of this lifetime. In fact, it's very significant. It's 4 sigma or something like that, sitting down here. So you can see there is some scatter in this. This is that experiment that came along much lower, and then started shaking things up in the field in this way. I guess initiated the puzzle. These two are our Los Alamos experiment. Basically, this was our commissioning data, so we didn't suggest that they include in the average. It doesn't have much pull anyway with the error bars. And then Patty 18 is our first physics result from our neutron storage experiment that I'll show a little bit later. So basically, this is the puzzle, and something that has to be resolved at this point. So to explain that a little better, I'd like to describe how the beam experiments are done. So basically, this is a cartoon that I got from someone, Scott Dewey, I think. And basically, these are, as I just showed, the cold neutrons go through this fiducial region, then they pass through a target. So you count the precise rate of the neutrons, you count the rate of the protons, and then that ratio gives you something that's the neutron lifetime, or the decay rate. And the principal difference between the beam and bottle is that the beam experiment, basically, it measures the decay products from the well-characterized neutron beam. It sort of counts the dead. It counts the ones that decay by their products. Okay, so how to measure that? I explained this a little bit before, but basically the trick is this 1/v sensitive detector. Its efficiency goes like 1/the velocity. And so you can take this proton rate that you expect. So you have your efficiency of your detector that figures in. then the integral over your beam fluence divided by V, and then the various factors that come in to correct that. So similar to the neutron beam, you have the calibrated efficiency of your detector, and then that same kind of velocity integral. So then the ratio of these you can use to determine, basically these things cancel out the velocity integral, and you end up with this. So you still have this efficiency of your proton detector and your efficiency of your neutron detector. And these have to be known absolutely, and that's the key challenge with this experiment is if you need a measure in the neutron lifetime to 1 or 0.1%, then you need to know your efficiencies to something like 0.1%. Okay, these all start with these cold neutron beams, which can be quite intense, and these are neutrons with kinetic energies less than thermal room temperature, basically, typically quite a lot less, like 20 or 40 Kelvin. They're produced from fast neutrons and then moderated down to the cold moderator. The nice thing about them is they can be reflected from polished materials, and so you can guide them down a pipe basically to your experiments. And you can furthermore have a curve guide, so you can reduce background from whatever your neutron source is. That's helpful for your detectors. And the nice thing about cold neutrons versus ultracold that I'll talk about in a bit is that you have lots of neutrons available, 10 to the 9 per square centimeter per second. So this is the best beam experiment that let's see, it was originally, actually they released the result in 2005, but it was updated. They readdressed their leading systematic and actually produced a more precise result later because the systematics have gotten smaller. So this again accounts protons from this beta from decays in flight. So the protons that are left over after the neutron decay gets trapped in this penning trap is called. So they have a strong magnetic field so that the protons spiral around. They're confined radially by the field, and then they have these electrodes to confine them in the trap. And so when they want to count it, they ground one side of this electrode stack, and then that guides out these protons, and then they're accelerated with a bias field into this proton detector. So this is what the key upgrade that they did that gave them what was published as a new result essentially, but it's basically the same day as the old one, just with that leading systematic much smaller. So they use this kind of clever technique to calibrate their this is their 1/V detector that they used in the experiment. And then this is the new calibration technique where they have this absorbing detector, and then they transfer the calibration to these various detectors to get an absolute result. So the proton detection, it hasn't been updated as far as I know, although I'll talk about their latest one in a second here. So basically protons are accelerated into this kind of 99%, one hopes, efficient detector. They have to apply corrections for dead layer and backscattering in that detector because they do need this absolute efficiency to be known. So the corrections were determined by some combination of basically measuring the dead layer with radioactive sources, taking data with these detectors with a thin coating on the window to enhance the backscattering, which is a loss. Then some combination of Monte Carlo calculations and extrapolation to zero loss. And so from this, they have what they think is a backscattering fraction versus their measured neutron lifetime. And so you can kind of see how they had to extrapolate down from that to have this green value, which is the result that they would report. Okay, so more recently, this experiment has been revived and run on a more intense cold neutron beam line. So it's basically the same experiment as BL1, but there are some improvements. In addition to the beam line, they've improved the proton trap electrode such that they can hold the protons in here for a longer period of time. And I guess they had problems with holding the voltage for longer than some period of time before, and so it's something about their electrostatics must have improved. So they've acquired production data and done many systematic studies with this trap. Haven't released any results yet. And then they want to evidently do a new trap with this, where they've actually blinded the length of their trap So their result involves turning off these electrodes to change the length, and you get a slope essentially. And so basically they hope for better pumping out of this as well. And so that's kind of an interesting thing, that they want better pumping. So one of the possible criticisms of this experiment is that residual gas in your system could be scattering your protons out of your trap. And so your efficiency is not as good as you think it is. So the way to test that, one way to do it, is to hold your protons for a longer period before you do this counting. And so, instead of like 3 milliseconds, or maybe hold it for 100 or something like that, or whatever the period that they want to use. And so by addressing that, I think they could be addressing one of the key possible criticisms of this experiment. However, like I say, they haven't been willing to share any results yet. So we can just look forward to that. So let's move on to the bottle experiments. So in this case, again, with this cartoon, so we measure the surviving neutrons in a confined population. It basically counts the living, or counts the survivors, you would say. So we don't care how they disappeared, we just count whatever's left. Okay, and these use ultracold neutrons, which have a lot of convenient properties for measurements of neutrons. So these are neutrons with kinetic energy less than a few hundred nano electron volt. So that's a velocity up to a few meters per second, basically. And the unique properties, they have total external reflection from common materials. For example, stainless steel has a pretty high, it's called Fermi potential. So it's like a step potential for them to bounce off of. Nickel 58 has a very good Fermi potential of 350 nanoelectron volt. So basically you can get a material bottle and you can literally fill it with ultracold neutrons and hold it in it. Furthermore, the gravitational confinement is to a few meters of height. So this gravitational potential is on this order also, this 100 nanoelectron volt per meter. So basically, if you have a 100 nanoelectron volt ultracold neutron, it'll bounce 1 meter high, up to 1 meter high. And you can furthermore change the kinetic energy by guiding it to a different height. The third kind of coincidence, I guess, is the magnetic potential is similar to kinetic energy with a few Tesla fields, so easily achievable fields in the laboratory. So, and that's due to this mu.B interaction of 60 nano electron volts per Tesla. So you can get total reflection from laboratory scale fields of one spin state, and then you get total transmission of the other spin state. So you can basically do 100% spin selection filter. And I do add one inconvenience is that it's hard to get a high density of neutrons, ultracold neutrons, into an actual experiment, though we've actually been doing a pretty good job of that lately. And okay, I didn't start my animation, but this is, imagine a 1 meter tall bottle. I just made them different colors for visibility, but that's more or less what they would look like bouncing around. Okay, there are a number of ultracold neutron sources around the world. The one that was operating for many years and still operates is at the ILL in France, and they produce a lot of these measurements, neutron lifetime and correlation measurements there over the years. Actually, the neutron lifetime one, anyway. Let's see, at LANL, that's ours. Ours is one of the few multi-experiment facilities, and it's also arguably the most intense ultracold neutron source in the world at the moment. So this is just showing our experimental hall. So we've taken away the shielding to show the ultracold neutron source. So it starts with protons that make spallation neutrons, and then we cool those down and eventually turn them into ultracold neutrons. Then those just kind of bounce around in these 4-inch guides, basically. And then it next down to 3 inches, no, 6 inches guide down to 4 inches. But the point is, it basically just diffuses out like an ideal gas in these vacuum guides. And then we can mount our experiments here. So here we have a superconducting magnet for a spin selection filter. So we have polarized neutrons coming out. And then that can go into our neutron lifetime trap. We, in the past, have had this beta decay symmetry experiment. So this is a 1 Tesla, several meter long magnet that we use for that. And we're building a new experiment, which is not measuring beta decay, but it's searching for another property of the neutron, which is the possible electric dipole moment. Okay, same thing in picture view, and this is actually an old picture. At the moment, we're building a big magnetically shielded enclosure for our new experiment on the electric dipole moment there. And that's just showing our tau over here on the right. And here the end cap is open, so you can, it's kind of fuzzy, but you can see the array in there. Okay, so as far as that cartoon of the fill, store, count, just for fun, we did exactly that, about as close as we can possibly do to a fill, store, count experiment, like the cartoon shows. So this is one of our staff here, Mark Mackley. He's holding it's basically a stainless steel pipe with end caps on it, and we've pulled a vacuum on that. And it has a thin window on the front of aluminum. So ultracold neutrons can pass through aluminum fairly easily. And so what he's doing here is he's holding it up to a thin window on our ultracold neutron guides, basically. And so some of them will punch through that window, then punch through this window, and then fill into this bottle. So I just play it. So he held it there for a minute, and then he turned it over and he's pouring it into a detector now. So basically with patience, it looks a little bit heavy, that bottle, but with patience, we could repeat that with different holding periods, and we could do a lifetime measurement with this bottle, although it wouldn't be very good. We'd have a lot of corrections to apply. And that's because all material bottles leak UCN to some extent. So you can look at the neutrons remaining after a time, let's say delta T, that's how long we hold it in the bottle after we fill it. And then the characteristic lifetime is this tau S, so tau storage, you could say. And that's related to this beta decay lifetime that we want. But then you also have to consider the rate of wall losses and then any other losses like gas upscattering. And so this is the important one for material bottles, this wall loss. That's some combination of upscattering from, for example, hydrogen on the walls, capture on wall materials, other interesting ways like these so-called quasi-bound UCNs, so they have a little bit too much energy to be contained by your material, and then any gaps that you have. And so in the end, you have this wall interaction loss contribution for some process that's proportional to, here it's called gamma, that's the rate, that's the wall collision rate, basically. And so how that's been dealt with in these material storage experiments is you vary that rate gamma, so you can extrapolate to zero wall collision rate and therefore zero wall collision loss. That's kind of shown in this equation here. So there are complications like how the energy spectrum evolves over time. You have to consider that either by design of your experiment or with a Monte Carlo or probably some combination. And different approaches have been used to vary this wall collision rate, typically by changing the bottle surface to volume ratio, like they did in this Mambo one. They had this kind of sliding wall, so they could do kind of a lifetime with one surface to volume ratio and then change it and then do a lifetime with another. There's another one where they kind of similarly did that. They had different bottles, and they furthermore measured the upscattered neutrons, and that gave them kind of a handle on the wall collision rate, and then they could use that rate to extrapolate to zero wall collisions. So there was one problem with that Mambo 1 experiment that I just showed, is that they had a more interesting loss on the wall than they originally expected. And so published in 2012, Starro calculated that due to this kind of anomalous wall loss rate here I'm plotting versus the incident energy to the wall, this loss rate, they have to account for this bump. What that did is it changed a major systematic correction, and it moved their result that they presented in 1989 down to this, where here it agrees quite well with the beam lifetime results, down to this 882.5, where it tends to come into more in line with the other bottle experiments. So now this is going to what has produced the most precise of these material bottle experiments. And I say material bottle because I'll talk about magnetic bottle in a minute. That's a Cerebrov experiment. So basically this is where he takes an open bucket. So he calls it the Gravitrop, because it's basically an open bucket where it's confined by gravity and then by the material on the sides and bottom of it. So this is a rotating bucket. So they turn this upside down with the opening facing the bottom. It's filled with these neutrons that come in, bounce around, and fill it up, and then they slowly can rotate it up when they're ready to take their holding period. And so they do that, fill it a bunch of times, hold it for a period, and then pour it out in the same way. And then they have a detector down here to count at the bottom to count the neutrons that have survived. And so this is just showing an example of the data. So here is their short holding period. So they evidently fill the bucket here, then rotate it up, and then you see these kind of neutrons on the side leak out. Then they have this short holding period, and they pour it out. And the reason it looks like this is because they poured it out, they kind of decanted it in steps. So they poured off a few of them, then poured a few more, poured a few more. The nice thing about that is it pours off different velocity cuts of the stored neutrons in general. So this is the same thing where they've held it for a long time, and you see, you know, far fewer coming out for a neutron lifetime. And so here's an example of their extrapolation technique. So they had two different size bottles. The bigger bottle, or rather the smaller bottle, is shown by these black points, and the larger bottle is shown by these. And the achievement of this experiment is that the shortest lifetime they showed, or rather the longest lifetime, this is an inverse lifetime on the left. The longest lifetime they showed is only a few seconds different than the final result. So their wall loss correction at that level was only something like 5 seconds, basically, that they had to extrapolate down. The other material bottle experiments tended to have 100 seconds correction, or they're, you know, one or 200 seconds is how far they had to extrapolate to get that final result. So based on that success, they built a Gravitrop II, it's called, and this one they had a more elaborate way of varying the surface to volume ratio and getting varying basically that wall collision rate. They could turn these kind of these volumes inside to the other one and either have this inner liner up or down, depending on if they wanted a higher or lower wall collision rate. And so they could then enable this kind of extrapolation here. Okay, unfortunately with Gravitrop II, in spite of its arguably better design, their coding was apparently not as good. So I tried to sort of overlay the two extrapolation plots here. So Gravitrop I, that's the 2005 result that had this 878. Gravitrop II, they have a somewhat higher result, still nowhere near the beam lifetime result, however. But basically, they unfortunately had to extrapolate quite far compared to their previous experiment. And so it's a concern. It means that this extrapolation has to be done extremely well. And this just kind of just making that point again, just showing the kind of corrections that had to be applied for these trapped ultracold neutron experiments. So they're in the kind of 100-second range that you have to do this extrapolation, and one hopes it's correct on the 1 second level when you get your final result. And then by comparison, this is the Gravitrop I experiment, and this paper, this is from 2011. It doesn't include the more recent ones. Okay, so the alternative to dealing with the wall loss is to try to eliminate the wall losses completely. And so this is the approach that we've actually taken at Los Alamos. So similar to the Gravitrop, we have gravity. We'll use gravity to confine from above, and however, we're using magnetic fields to confine it below and laterally. And so what we can do is with an appropriate magnetic array on the bottom. This is just showing the strength of the field. So you could, for example, look at this 0.8 Tesla line. And so this doesn't get closer than 2 millimeters to the material surface. And so we can drop a neutron from say 50 centimeters. It'll come down, come within as close as 2 millimeters to the surface, and then bounce off without touching any material. And so there's no possibility for loss from material interactions that way. And this is just showing the trap we built. So it has these stripes indicate different magnetization directions. It's in this kind of rotating magnetization direction Halbach pattern as you travel, in this case, from the upper right to the lower left. It has this other feature in that it's asymmetric. So it's this bowl that's asymmetric. And we think that's a big advantage for removing neutrons that are a little bit too fast to be stored well for long periods of time. And so that was actually one of the keys. And so this is just showing the scale. It's a couple of meters long and 1.5 meters wide, something like that. And so furthermore, while we've gotten rid of the wall interactions, we do have to make sure that we don't depolarize UCN, because we're only trapping one of the spin states, the ones that are repelled by high fields. And so we basically ensure that by superimposing another magnetic field perpendicular to the array, such that we have no field zeros where you could get depolarization and loss. The other key feature of this, which is new for these lifetime experiences, is that we don't drain the neutrons out the bottom. Instead, we bring a detector to the neutrons. So we lower this active detector down from the top, and then it has a boron 10 surface that soaks up the UCNs, that kicks off a lithium and an alpha, and then that's detected by a scintillator that's behind this boron 10. So that's both very efficient, and it also avoids any possibility of weird effects that could change how we count with a long holding time versus a short holding time. For example, you could imagine a neutron that gets kicked into a high angular momentum state, orbiting around this drain for a long period of time before it actually comes out. That could conceivably be different between short and long holding periods. So by bringing the detector to that, we just soak it up and it doesn't matter. Okay, so we released our first result in 2017. It was published in 2018 finally, and that just shows what we have. So the key difference between every other storage lifetime that's come before this is that our systematic correction was much smaller than the statistical spread in this. So basically, we have a zero offset on this. So the storage time in our magnetic trap is the beta decay lifetime as far as we can tell. So more recently, actually very recently, it was published in October 13th, is our new result. And this is now by far the most precise single measurement. And it still has the quality that our systematic corrections are very small. The only corrections we had were from residual gas scattering, and we actually think that's pretty accurate. But it's still, that's only a third of our statistical uncertainty at the moment, and we can furthermore make that better. This aluminum block one, this is when it's literally an aluminum block, a little block that fell in our trap for some of the data. We were able to correct for that, we think, very accurately. So that's why there's that little offset. Still much smaller than statistical uncertainty that we're reporting. Okay, so let's go back to the world data, and now including our new result. So we have the Cerebravo 5, let's see, the Starro 12, which is a corrected older experiment. I believe arisen, one of these that was also corrected down. It used to be higher, and then a new systematic error was found that they did the solid angle wrong for the detector, and so that shifted it down towards these results. Which is, so basically the bottles are now in not terrible agreement. The new Cerebravo result, the Gravitrop II, it actually came in somewhat high, which does contribute to some tension in these results. In the more recent particle data group averages, the beam experiments are just excluded as outliers, and so I think they just decided that that bottle's probably right at this point, at least as far as they're going to compile it. So when our new result gets included, that's going to tend to pull the average down still more, notwithstanding how much the error has to be spread to account for the tension. And so this is where our new result would sit, just kind of extremely well in agreement with our previous result, which is this Parity 2018. EJOV, by the way, is another magnetic trap. It's with a somewhat different approach, where they didn't have, they may have had field zeros that they had to correct for, but still they had a storage time very close to the beta decay lifetime, and they are in agreement with our experiment, and pretty good agreement with the other storage experiments, not in agreement at all with the beam experiment. Okay, so the question is, just getting back to the beginning, can we test the standard model with neutron decay yet? So just referring to that master formula where we have relates this VUD quantity that we want to measure that unitarity to the experimental lifetime tau n, and then the GA also experimental, and then this about 4% radiative correction that you have to consider for quantum corrections to this process. So here, this plot, I'll show it a few times, so let me explain it. So I'm plotting this VUD determination versus this GA parameter. so basically there have been several GA measurements. The more recent ones are this, we call them post 2002. One of them includes ours at Los Alamos using ultracold neutrons actually. The PDG, however, still insists on including these older experiments, which have may have larger systematic corrections, or may not, or may have larger backgrounds, or something. But at the moment, they can't be excluded by the data alone, by the results alone, as outliers. And so these still kind of contaminate the GA results. But if we just consider these kind of post 2002, the more recent GA experiments, then that would be this kind of cyan band. So VUD can also be determined by this nuclear decay, as I showed before, and that's this kind of red band. And this is old. I'll show an updated version actually, but the experimental result here, and this has to account for nuclear corrections as well, because here the neutrons are bound up in a nucleus, and so you have to consider that environment and correct for that. Unitarity, if it's correct, would be this kind of gray band, and this is just kind of assuming unitarity is correct. And so the lifetime based on this curve, so you have a constant lifetime, so VUD versus this 1/1+3 GA squared, that's in this range, it just looks like these diagonal bands for a given neutron lifetime. And I'll say in this plot, I haven't included the 2021, our most recent UCN Tau result. I just put our result separate here rather than the complete PDG result. Okay, a few years ago, there was a reevaluation of that radiative correction term, and actually shifted it very significantly from what it had been prior. So basically, they did some kind of dispersion relation calculation to relate it to other types of measurements, particle physics, and they come up with a new value, which is a lot different. So if you look, I guess you have to look in detail, but basically it's more than the reported error of the previous radiative corrections. And here's what that does to that plot that I just showed. So this impacts neutron and nuclear decay, by the way. It's kind of a universal radiative correction to this process. So what it does is it breaks unitarity. So now if we take VUD from these nuclear decays, it's this class called 0+ nuclear decays, it does not give you the answer, the correct value that would make unitarity true, basically. And so that's maybe a totally different puzzle. It's not usually what we say by the neutron lifetime puzzle, but this is, I think, what we should be interested in as well. So neutron decay isn't quite there to be able to comment on it. So that would be if we, again, ignoring the old decay symmetry experiments. If we take, for example, our result from 2018, 2017, and try to, well, I guess by eye do an ellipse here with the GA, we can't really tell the difference between the 0+ result and then what it has to be for unitarity. Not quite yet. Okay, so here's if we add our latest Tau result and try to do the same thing. So here again, it's really close. I mean, if our results alone are, yeah, it's probably not enough error bars to conclude anything. So we're getting there, but we need to, at this point, improve the precision of all experiments, both GA and the lifetime. Okay, so what about this beam versus bottle? So there were many publications in 2018. This was actually, so that radiative correction update was published late in the year. So this is not taking that into account. This is mainly just looking at this glaring beam versus bottle puzzle or issue. And so basically the question is, it started with this paper from Fornal and Grinstein that actually saw that Grinstein had given a colloquium here back in September, which I wish I had seen. But so you guys may know a lot about this already, but the question is, could the neutron beta decay branching ratio be less than 100%? So in the standard model, that's the only way they decay. So it should be 100%. And so what they suggested is that what if you had a 1% of the time, say, a decay to a dark matter particle? And what they worked out is that a possible signature for this would be a photon with this energy in kind of this 1 MeV range. Another possible signature would be an E+ E- pair with again, less than this kind of 1.6 MeV range. So this came out on the archive in, I guess, January, maybe early January. We had about 2 or 3 weeks of beam left. So we set up a germanium detector by basically a bottle of neutrons, ultracold neutrons that was in our beam line. And this has actually quite a few neutrons in it. And what this germanium detector does, it looks for that photon. So we looked specifically for this signature that they suggested just because we could, basically. And so what we found is here, we published it. Actually, this is led by Xiaowen Tang, another staff scientist at Los Alamos here. Basically, this set a limit on the branching ratio of 10 to minus 3. So not actually less than that, 10 to minus 4, I think. So basically, we didn't see the signature. It's so if you put a kind of a conjecture, a proposed dark matter peak anywhere, we didn't see enough. We were able to account for all of these other peaks as expected background events in this window that we would expect. So at least at the 100% level, that's not what we would see. Furthermore, as far as the E plus E minus decay signature, for that we had data already in the can from our it's called the UCNAs, that beta decay symmetry experiment. And so one actually graduate student at Caltech reanalyzed that data looking for this specific signature, and he was able to rule that out as well. And so at least in that way, it's not about. The other reason to question that proposal is that okay, the neutron decay to dark matter is probably inconsistent with observed heavier neutron star masses. I put an asterisk because you can always work around that. The asterisk basically is unless the dark matter particle is strongly self-interacting with specific constraints on this interaction, and that's probably what Grinstein talked about a couple months ago. And so basically, after that came out, pretty much right away, there was this paper that came out, say it's light dark baryons are excluded basically because you can't have neutron stars that go to mass 2, basically two solar masses. Okay, similarly, same issue of PRL, another group came up with the same conclusion. If a neutron can decay to a stable, feebly interacting dark fermion, the maximum possible mass is 0.7 solar masses, while all well-measured neutron star masses exceed 1 solar mass. Okay, so however, and again, this is why I wish I had seen that colloquium the other day, or a couple months ago, that there may still be scenarios consistent with neutron star observations, but you have to look at the complete set of observations, I guess, to see if that's if that can still work. So basically, in this letter, we demonstrate that the appropriate dark matter baryon interactions can accommodate neutron stars with mass above 2 solar masses, and then. So anyway, there are always ways to get around it, but you have to have evidently self-interacting dark matter to do that, so that you can have the mass that you want in the end. Another reason to prefer one beam or bottle versus the other is that you can look at other beta decay measurements and try to come up with a consistent picture. And so this was the argument that Czarnecki, Marciano, and Serlin made, is that the bottle lifetime is consistent with other beta decay measurements. So basically, if you take the GA from from our beta decay symmetry, or you can take the GA from muon capture on the proton, that's consistent with that, which has also been measured quite well. Then you find that it really strongly favors the bottle lifetime, the 880 seconds or so. And so basically, they were able to, on that basis alone, put a general constraint on this, as I say, exotic neutron beta decay branching ratios of less than 0.3. Okay, and just kind of pictorially, what they're saying is that if you believe the beam result, then that puts your GA way over here versus the bottle result seems to be pretty consistent with what we prefer for the GA values now. Okay, however, one could argue that it's an experimental question, so it should still be measured. So new idea is this ultracold neutron experiment for a proton branching ratio and neutron beta decay. And this is, again, this is by Xiaowen Tang, who's proposed this and has been a proponent of this. So basically, we're trying to see, can we do a beam type measurement that is an absolute measurement of the decay products coming off from a known population of neutrons. And so we could build something like this box. And so here you make a a box out of this scintillator material that also has a good Fermi potential to store neutrons. So you load in neutrons here, and then let's just go over to the right to this plot, and so you see these decay products coming off. The electrons are easier in this case to measure because they have enough energy that they can make a signal in the box. And then after some set time, we say, okay, how many neutrons do we have in the box? So we flood it with helium-3, and then we have neutron capture on helium-3, which then kicks off triton and proton, and then that makes a signal in your scintillator. And so basically that gives you a determination of the number of neutrons in there. And so you can kind of count the decay products, count the neutrons in there, and from that you have the branching ratio or the decay rate. And so it's probably hard, but we're right now in, I'd say, our R&D stage to determine feasibility of doing this, of if we can get a measurement that's equivalent to 1 or 2 seconds uncertainty, which would either confirm or not the beam lifetime result. Okay, so that's going to the summary. So basically, with neutron beta decay experiments, we're approaching a level of precision that tests the standard model of particle physics. With upcoming experiments, we can confirm or not the disagreement with that first row CKM unitarity when using DUD from super loud beta decay. There is good agreement among the UCN bottle experiments, notwithstanding that tension, a little bit of tension. And each of those, I will remark, use quite different techniques. I mean, especially the material bottles versus magnetic bottles is pretty different. The beam lifetime experimental results, that's still a puzzle, and I think we just have to wait for BL2 results, or given enough time, we'll do the UCN probe experiment here. All right, thank you.
Well, thanks for a very good talk on this subject. You've clarified a lot of things for all of us, I think. Let's open it up for questions. We can use the chat box or just raise your hand or shout or whatever.
Hi, I did have one quick question, Steve.
Mm-hmm.
If you can go to, I think slide 50, where you show the last time you showed the what you called the master equation. Yeah. So I've read recently some reports where they consider a changing fine structure constant, alpha, and how that is related to the neutron lifetime. But in your decay formula, I don't see where that would come in. Could you maybe comment on that?
Alpha.
Or I guess just in general, how the fine structure constant may be related to neutron decay.
That well, I don't know. I mean,
okay.
I think that's electromagnetic, but yeah, I'm sorry. I think it probably gets folded into here somehow with some of the things that pop up in that radiative correction. I don't think it'd be in leading order here, but yeah, I'm not sure.
Awesome. Yeah, sorry, I didn't mean to ambush you with a question in the left field there, but thank you.
Sure.
Let's see, we certainly have time for other questions. Does someone have a question? Well, I must say I'm a little disappointed that you've quoted a bunch of theory papers that do seem to strongly favor the bottle experiments and therefore seem to rule out the possibility of decay into dark matter.
Well, yeah, maybe. I mean, you'd have to, it could be something completely different too. I mean, yeah, and there was this response by Grinstein and others that they can find a way to make it work.
it's sort of too bad. We've had this dark matter around for 90 years and or 88 years, and we don't have any earthly detection.
Right.
So I was rooting for the beam experiment, frankly.
They should have a new result out. So I think in another year, maybe, whenever they're comfortable doing it. I mean, they're probably very cautious about releasing another result.
They is who?
It is the group at NIST, Gaithersburg, and
I
University
see.
of Tennessee.
Gaithersburg and another group also?
Yeah, it's Tennessee, Knoxville. So Nadia Foman's group used to be, Jeff Green is now retired, but he was a big proponent of this. Jeff Nico at NIST would be another contact for that one.
Right. So is there another question? Well, let's once again thank our speaker for an excellent summary of the situation. And I guess we can look forward to the NIST and Tennessee results that in a year or two, and more results from Los Alamos. As I say, I think Congress ought to pour some money into this, because I think it is an embarrassment to the Department of Weapons of Mass Destruction. Anyway, so thanks once again for bringing us up to date, in a sense, on this subject. It was a very clear, very good talk, and
Thank you.
we're all very grateful. Thank you.
All right.
So I'm going to end this thing then, or maybe Ed will end it. I guess I can't really control things. So goodbye.